I'd like to invite Yi Li to return to the presentation. This is the presentation that is transferred from parallel session 5. And Yi Li will talk about computational simulation of clothing mechanical behavior with an improved particle model. We saw in the first presentation how it is possible to develop an enhanced view of modeling the human body, tactile sensations, and to relate this to mechanical and other properties of textile materials. And this second presentation promises to take this a step further. So, I assume we've just got to let this warm up, and then you'll be able to present.
In the first presentation, it's really the screen does not work. In the first presentation, we have seen we can do the modeling simulation, carried out analytical or computational analysis how the body interacts with the body, interacts with the garments. Then we can carry out the engineering design. Well, how do we do that? Okay, and what's the model about? And that's the what we're going to discuss in this presentation. Dr. Dai is a postdoc research fellow on this, and she cannot come on this special occasion, so I present for her. In this model, we develop a computational methodology to simulate the mechanical behavior of the garments on the human body, including the sewing process. But how do we do that? We use a particle-based model, where the particle model is improved with a given aspect. Very well. In terms of the first analysis, the forces which we wear the garment. That's including the internal forces in terms of the shearing, tension, and tension, compression, bending, so on and so on. Meanwhile, they have a contact force from the body to the garment. Also, inertial force of the mass of the garments as a gravity as well. Also, the frictional forces between the garments. Also, the internal frictional forces between the fibers and yarns. For this one, then we can simulate on the basis of this mechanical or physical model of the garments on the body. Then we can simulate the features of the mechanical behavior. There is many different ways to simulate. Like we have finite element model, we have finite volume model. Now there is another one is discrete data model, which is called a particle model. For instance, in the 1990, by Brin, he proposed a particle model which used a square or as the element of the model, which is presenting the weft and the warp directions. From this, he generates use the springs to consider the relationships between the particles, like by separation, compression, and by this one is by bending and shearing properties. In this model, there is some advantages. It's able to illustrate the effects of the molecular properties, also the orthotropic features of the fabrics, like in the weft and the warp directions. However, we have problem in terms of the model. First, the twisting effects was ignored. Also, the calculations of the forces and the torques are based totally rely on the mechanical measurements from the Kawabata system, which only work for the small deformation sort of situation. Therefore, there is another work which needs to be carried out to modify the model. Why using this phrase on the shear, simulation of the shear, they show that on each particle, the shear is under one plate, under 2 dimensions. So they use the change of the angles to simulate the shear. But in a practical situation, the garments actually is a 3-dimensional. So besides that, like an X, Y dimension, there is another dimension, the Z dimension, which calls the shearing features of the garments. So we started to kind of see the model itself. Sorry.
Somebody is trying to help us. I can't
Okay. So anyway, one issue is the extension compression, which we start from the fundamental work of like a relationship between the elongation and the loadings, and which we can simulate this from analysis, which basically the model is presented as the force is proportional as the Young's modulus and the deformation itself. So it's Foucault laws which applies to this one, to extension and compression. For the extensions, we know the tensors, but for compressions, very little work has to be done, not reported. However, we normally consider that equivalent in the reverse directions. So that's the assumptions which we use for this one. Another one, again, I cannot say very clearly on the PD. That's the bending torques. How do we, the bending torques, which is also considered to be proportional to the bending rigidity and the deformations in terms of curvature. Then the bending rigidity can be derived from the measurements of the bending load and curvature, which similarly results you can find from the bottom measurements. But the deformation can be in the large deformation, therefore don't have to follow exactly as the Kawabata PES measurements. In other words, shearing information, we have considered a square of 4 particles. And if we look into the total of, if the particles can be like a piece of paper, can be bending in the different dimensions. So one issue is we consider to across that diagonal crosses become 2 triangles. And on a triangle, it becomes 1 plate. So the shearing angle on the plate becomes the shearing deformation, which again, the shearing deformation is a proportional, again, another equation is not here, it's a proportion of the shearing rigidities and the torques which work on the shearing dimensions. The twisting effect is actually in another dimension. If you count 4 particles in the warp and the weight direction, you consider the torques which I said for twisting is in another dimension. So you can say like this. So the torques is proportional to the torque rigidity and the deformations. And for the torque twisting rigidity, which we do not have the measurements. However, they can derive from the relationships of the bending rigidity of the warp direction, as well as another directions. So from this model, we generate use C a class to write a computer program to carry out the analysis. From analysis, we simulate and validate these predictions by use 2 different experiments. One is use hard loop, which we have considered the separation of the brain, tension, compression, bending, shearing, twisting, extension, and the motion equations. So that's the features like of this hard loops. Using hard loops, like you cut into 2.5 meters, and it's 25 lengths in total. And so together, then the drape length is become a measurement of the bending and rigidity of the fabric. So we compare this in two dimensions. One is in cut in the warp direction and the web direction. Another one is the across diagonal directions. So we carried out the measurements in and simulated three different fabrics: a thin wall, and a thin cotton, and a thick cotton. That's the fundamental mechanical properties which we measure using this system. So that's the measurements. Thank you very much. That's the measurements we compare with different models. That's the original Reese model published in 1990. You can see that that's the actual measurements. For this one, we only modify the model with the bending torques. Okay. From this you can see the original model cannot simulate very well with the shape of the experimental draping effects. With the improvement only on one component on the bending equations, we have a good simulation prediction of the draping effects. By analysis the stresses in the fabric, we can see we have a tension which from the dark to the light, and the color indicated the stress is increasing. And we can see the tension compression is important, bending is important. However, the shearing effect is not important in this situation. Then we carry out another analysis on the bias direction, the specimen. From this one, that's the photograph of the experimental results. Then we use the improved model, only use improved with the bending torque. You can see it's basically okay, but it's somewhat different from the actual experiments. With this one, we improved with the bending and shearing. Then it's does not improve too much. However, when we consider the bending shearing together with the twisting, it's become very close to the experimental results. By analysis of the models, the stresses in the model, in the fabric, we can see the bending compression change dramatically. Bending is also important. Also, importantly, shearing is important, and the twisting has significant effects on the draping effects. So compare the photographs with different dimensions. We can have similar results compared with the photographs. The new model we proposed has a good simulation of the actual experimental results. That's the one for thick cotton, where similar results has been achieved, whether for warp direction, web direction, and bias direction. Further, we use this one to simulate the garments. What I'm going to have is a body with inside like this. Then the people have a very simple pattern to carry the fabrics and just fold the arm to become a skirt. And the result is that we can see the draping effects visually to say the patterns. Whether that effect is only really for illustration or compare with the actual garment, whether that's true. This is what we are analysis to see whether that's the case. So we carry an experiment and analysis for the same iron fabrics with two different dimensions of cutting. One is on the y direction and the web direction, so cutting this way. Another one is we cutting the diagonal or bounce direction. That's the wall and that's the web. We cut in this shape. Then with the same pattern, they have different features of the draping effects. That's the photo. You can see the different patterns of draping. But with the similar results, you can, it's not very clear here, but as I can simulate basically the same patterns of the draping effects. And also for the bounce dimension, the cutting, the patterns of the stress skirts, front view and back view, also can be similarly characterized relatively accurately by the similar results of the model. So in this paper, we present a detailed work of the model development, which is a new particle model has been developed with significant improvements in the simulation accuracy with good experimental validation, hard loop deformation, skirt construction, and draping effects, which the improvement is on stress-strain relationships, also considering the twisting effects. Thank you for your attention.